Hi all, today we are going to discuss about current transformer. So the current transformer is mainly used for extending the range of instruments, that is extending the range of ammeter, as well as it is also used for extending the range of the wattmeter, as well as providing the current input for the release. So how it will be given? Let us take, for example, I am taking a transmission line. So let us assume there is some load, and let us assume the current rating of my system is very high. Let us assume this is my primary side voltage, and the primary side current, let us assume I am representing by IP. So CT will be connected like this. CT will be connected, the primary winding will be connected in series with your line. As this winding is connected in series with your line, because when the current is passing through something, because of the resistance there will be voltage drop. So that voltage drop or the effect of this CT on this line should be as minimum as possible. In order to avoid the voltage drop or the effect on the main system, it should have the minimum possible number of turns with more thick wire. That means it should have the minimum possible resistance so that the voltage drop will be minimum. And now it will have a secondary winding. So secondary winding will have more number of turns, which will be connected to the ammeter if you want to measure the current. If you want to measure the power, it will be given to current coil of the wattmeter, or if you want to connect to a overcurrent relay, it will be connected to the relay coil. So in all these cases, the coils or respective coils are in such a way, they will act nearly as a short circuit. Let us assume the primary number of turns are N1 and secondary number of turns are N2. As the primary side, the current IP is passing. So in this transformer, the working is completely different that of the normal power transformer. So I have briefly explained in last class, same thing I am repeating once again. So this IP and N1 are passing in the primary. So the magnetomotive force or MMF that is produced in the primary side, I am writing as MMF1 is equal to N1 multiplied by IP. So because of this MMF, the flux will be produced in the core. That flux will link with the secondary. So in the secondary side, EMF will be induced and the current will start passing as per Lenge's law in such a way that this secondary will produce the exactly same flux or the same MMF, so to counterbalance the primary MMF. That means the net flux in the core will be only equal to the no load component or magnetizing component only. So the secondary MMF will exactly counterbalance the primary MMF as per the Lenge's law. So in the secondary side, the MMF that is produced will be equal to N2 multiplied by IS. So N2 multiplied by IS. So here you have to remember that primary side current is not decided by the secondary side, because primary side current is decided by the load. This current cannot change which is passing through the primary. So the primary MMF is only dependent on your load, which is N1 multiplied by IP is decided according to the primary MMF. That means how the IP is changing, accordingly the IS will change in the secondary. So here this MMF1 should be counterbalanced by the MMF2. So because of this reason, this one I can write as N1 into IP is equal to N2 into secondary side or IS, or this I can write as the secondary current that is induced will be equal to N1 divided by N2 times of IP. So here you have to know that whatever the current is induced in the secondary side, that is independent of the loading on the secondary side. So that you have to take care. And the second one, in order to safeguard the personnel who are operating this equipment, so what we generally do, one terminal of your CT is always grounded in order to protect the personnel. That means by mistake, even if the insulation is removed or disconnected, as it is connected to ground, this will be at the ground potential. The person who is operating here will not get affected. This is done for safe side purpose. I think this is clear up to now. So now I am summarizing from here, the CT should be like that. The primary voltage drop should be as minimum as possible, because so that the circuit characteristics are not changed, and the secondary burden or the secondary load that is connected in the secondary side should be as minimum as possible, so that this is not going to create any type of errors in the CT. So how the errors are created because of all these things, so that I am going to discuss today's lecture and the next lecture. So let us proceed further. So this current transformer I can represent by equivalent circuit. Equivalent circuit will be similar to the normal transformer only. Only the difference here is the primary current is not dependent on the load. The primary current is independent of the load. Let us assume the burden or the load, that ammeter whatever is connected. So that impedance I am representing by Re plus jXe, that represents the impedance of your load, and this Rs and Xs indicates the secondary side impedance of your current transformer, because secondary winding will have the resistance as well as the leakage reactance. Some leakage flux will always be there. This is Rs plus jXs, and similarly the primary side, the resistance and the leakage reactance I am representing by Rp and Xp. In practice, the leakage reactance is always maintained as minimum as possible. The winding is done in such a way this Xp will be very less. Similarly, the Xs also will be as minimum as possible. Similarly, the value of Rp, that means primary side winding resistance, will be nearly equal to 0 because it is made up of one turn or two turn only, in order to decrease the voltage drop or having the effect or the effect on the line. Getting it? So now coming to the secondary side winding will have the resistance, so that Rs will be there. Similarly, your ammeter load, whatever the load is there on the secondary, that will be mainly taken care that it will be mainly resistive load only. So always it will be taken care that the secondary side whatever the burden is there, that will be mainly resistive. So that care will be taken care. So now coming to the primary side, because no core is not having the infinite permeability, it will have the finite permeability. So core will take some magnetizing component of current to produce the magnetization or to produce the flux in the core. And along with that, as we are giving the sinusoidal input, so always there will be core loss in the core. That core loss component I am representing by Rc, and the core loss component of current is Ic. Or we can tell this no load current component will have two components. One is Im and second one is Ic, and this angle I am representing by the angle alpha. So now coming to the secondary side, let us assume the secondary side induced EMF I am representing by Es because of the current passing in the primary. So this Is will be lagging behind Es, let us assume by some angle delta. So this delta indicate phase angle between Es and Is. If you go to this phasor diagram again, the phase angle between Es and Is will be due to the impedance. What is the impedance? Impedance is Xs plus Xe, that is the reactance, and resistance will be equal to Rs plus Re. Or we can tell that Xs plus Xe will be the reactance and Rs plus Re is the resistance. So tan inverse of Xs plus Xe divided by Rs plus Re, that gives my angle delta. So delta is clear to you. So now depending out of this current that is passing, because of the current out of this Es, some drop will be there across this Rs plus Jxs. Rs plus Jxs, remaining voltage is coming at your terminal, that is Vs, or otherwise we can tell that Vs plus Is multiplied by Rs plus Jxs. So that gives my value of Es. Actually it is the inverse process. Out of the Es, there is Isxs drop, Isrs drop, that gives your terminal voltage Vs. So now the angle between this Vs and Rs, that means this is Vs and the value that Is is the current passing through your ammeter or the load. So this is called as the load power factor angle. That load power factor angle depend on the load impedance. That means it will be tan inverse of Xe by Re. So that I have represented here. Beta is tan inverse of Xe by Re, and delta is the angle between E2 and I2. And similarly, I am defining one more term alpha. That alpha is this primary side angle between the flux or Im and I0. So this angle is called as no load angle. So now this current Is referred to the primary side, I am writing as N times of Is, because it will be transformed according to the turns ratio. So this N times of Is plus I0, that gives your total primary current. So here you have to remember in the CT, Ip is not decided by Is. So Ip is fixed, and according to I0, N times of Is will come when this referred to the secondary side, and accordingly we have to draw the diagram. Here Ip is fixed and all the other components are designed accordingly in the CT. You have to remember this one. So let us assume the turns ratio I am representing by Ns by Np. So let us proceed further for the analysis. So that in the primary side whatever the curve is coming, that I have represented here. So let us try to analyze some angles. Here this OA indicates N times of Is, and this OC indicates the primary current IP, which is the sum of N times of IS plus I naught, because this I naught I have drawn parallel here, or we can tell that the component AC or the vector AC is nothing but equal to I naught. So now I am extending OA and I am drawing a bisector from here, that means a perpendicular line from here such that it will intersect at IP, or we can tell this a triangle ABC will form a right angle triangle. So now I can calculate my value of AB. So AB will be equal to, this component is I naught cos of the angle. Similarly, BC will be equal to I naught sine of the angle. So what is this angle? So you can clearly observe here, this angle is nothing but the angle between this is I naught and this is N times of IS. That means this angle is nothing but the angle between these two. That means that angle is nothing but this angle. The same angle will be here. So the total angle is 90 degrees. So this angle will be equal to 90 minus, out of 90 you have to subtract alpha and delta. That's why this angle will be equal to 90 minus alpha minus delta. I am repeating once again, because we know the total angle is 90 degrees. The angle subtended here is the angle between, because this component is I naught and this is parallel to value of N times of IS, or this angle is nothing but the angle between I naught and N times of IS. How can I calculate it? This total angle is 90 degrees minus, so what angles are there? Because I have to calculate between I naught and N times of IS, this will be equal to alpha minus delta. So that gives this angle. So from this I can calculate the vector AB. So each vector I can calculate. So angle BAC is equal to 90 minus alpha minus delta, and the value of AC, the value of AC is nothing but equal to I naught. The value of OA is nothing but N times of IS, and the value of OC is nothing but equal to IP. So from this I can write the value of BC will be equal to I naught sine of this angle, sine of 90 minus delta minus alpha. So this I can write out sine of 90 minus of alpha plus delta. So this will become sine 90 minus theta is cos theta. So this becomes I naught cos delta plus alpha. Similarly, I can write my value of AB. AB will be I naught cos 90 minus delta minus alpha. This is I naught sine delta plus alpha. So from this I can write my, in this right angle triangle, that means right angle triangle OBC, I can write as OC square is equal to OB square plus BC square. OB is nothing but OA plus AB whole square plus BC square. I am just substituting the value of OA, AB and BC here. So I have substituted here and expanded them. So when you expand them, you can see here I naught square sine square delta plus alpha is there. Here I naught square cos square delta plus alpha is there. So we know that cos square theta plus sine square theta will be equal to 1. So we can sum them. So when you are simplifying this one, this becomes N times of IS square plus I naught square. I have taken these two components together, which will sum up to 1, and this component I have written here. So finally the term becomes this one, that is equal to IP square, because the value of OC is nothing but equal to IP. So from this IP I can calculate as square root of this one, or we can tell this term to the power of 1 by 2. I am taking this as equation number 1. So let us try to calculate the transformation ratio. We have already seen the transformation ratio in the last class. Transformation ratio is the ratio of primary current divided by secondary current. That is the actual primary current divided by actual secondary current. So primary current we have calculated from here. So I have substituted here divided by IS. So in a well designed transformer, generally the no load component of current will be very less, negligibly small, because we have to will take care in proper designing of the transformer, because I am going to prove in the coming derivation that because of this I naught only the errors will come in the transformer. So that's why this I naught should be as minimum as possible. So practically this I naught is negligible. So even if you multiply this I naught, because as it is negligibly small, even if you multiply with some factor, it is not going to affect the result. So that's why this I naught I am multiplying with sine delta plus alpha. That means here wherever I naught square is there, I can write as I naught sine alpha plus delta whole square, because it is not going to affect my result so much, but this equation will become so much simplified. Because when you add this sine delta plus alpha there, this of the form a square plus b square plus 2ab form. So this will be equal to a plus b whole square. So to the power of 1 by 2 I can simply write as a plus b. So in that form. That is the reason. So when you simplify this one, this will become equal to n times of is plus I naught sine delta plus alpha. It will simplify in that form. So this is n times of is plus I naught sine delta plus alpha divided by is. That is the transformation ratio. So this I can simplify. N times of is by is is equal to n, and second term is I naught by is sine delta plus alpha. So this sine delta plus alpha I can expand it. Sine a plus b is equal to sine a cos b plus cos a sine b. So when I am expanding this, you will get it like this. We know that the value of I naught cos alpha. So you can see the diagram here. I have to read on the diagram here. This I naught cos alpha, this is alpha, this becomes the magnetizing component. Similarly, I naught sin alpha will become the core loss component. So that's why I can replace those terms. I naught cos alpha I can replace with magnetizing component of current Im, and I naught sin alpha I am replacing by core loss component. So finally this R come as n plus Im sin delta plus Ic cos delta divided by Is. So you can see here the transformation ratio is not equal to the turns ratio, but it is something different. One extra term is coming. So this gives rise to the error. So there comes the error. That error is represented by the term called as a ratio error, because this indicates what is the error in the ratio. So this ratio error is given by nominal ratio minus actual ratio divided by actual ratio into 100. Or this nominal ratio we have seen in last class is nothing but given by k suffix n minus r by r into 100. What is this nominal ratio? Nominal ratio is rated primary winding current divided by rated secondary winding current. This is nothing but equal to the turns ratio. So that is equal to n. So when I am substituting there, this becomes n minus r divided by r into 100. So in practice, the CT burden is largely resistive. So secondary phase angle, that delta will be very small. So again I am going back to this diagram. This secondary phase angle, this delta, that means the angle between the secondary induced EMF and the secondary current, because when it is referred to primary it is same. So this delta in practice will be very less, because mainly it is designed to be resistive. So that's why this value of delta is very less. So I can take sin delta approximately equal to 0 and cos delta I can take nearly equal to 1. This introduces very less error only, so it is acceptable. So this equation number 4, which is equal to n, the transformation ratio we got as n plus Im sin delta plus Ic cos delta by Is. So sin delta I am replacing with 0, cos delta I am replacing with n. This becomes n plus Ic by Is. So now from this I can calculate my ratio error is equal to nominal ratio is n minus transformation ratio is n plus Ic by Is divided by n plus Ic by Is. So in practice, the value of n or the turns ratio is far greater than Ic by Is, because Ic is very less when compared to Is. So that's why, because core loss component is very less. So that's why this n plus this one I can replace with n. So I have replaced with n, and this numerator become Ic by Is. So we will get this approximately equal to Ic divided by n times of Is into 100. So you can see here the ratio error is coming as the core loss component of current. That means we can tell that the ratio error is mainly due to core loss component of current, or the core losses in the core. So this is one of the interview questions, or in the competitive exams they will ask in the CT the ratio error is introduced due to. The ratio error is introduced due to the core loss or the iron losses in the current transformer, that is equal to Ic, that is core loss component of the current. So now coming to the second error that can come is phase angle. This phase angle error is significant when you want to use your secondary side of the CT is connected to the current coil of a wattmeter. Whenever it is connected to the current coil of a wattmeter, how the wattmeter will measure the power? Wattmeter will measure the power by the product of voltage multiplied by current multiplied by cos of the angle between them. You agree with me? So when there is an angle between, because actually whatever is the angle between voltage or the primary side current, if it is not referred exactly to the secondary side, some error is introduced. Because of this, automatically the power that is measured will be wrong. Or how the error will be minimum? Ideally speaking, the value of n times of Is should be in phase with the primary current. That means this n times of Is or the secondary side current should be actually 180 degrees opposite to the primary current. But in practice, it is not same. Some angle is introduced. So the angle difference between the primary current and n times of Is, that is called as the phase angle or the phase angle error. So this phase angle I can write as, from this equation I can write tan theta. Tan theta is nothing but opposite by adjacent. So what is opposite? Opposite is BC and the adjacent is equal to AB. So sorry, OB. So this OB I can write as BC divided by OA plus AB, or this I can write as I naught, because BC is nothing but we have already derived, is I naught cos alpha plus delta, and OA is nothing but n times of Is, and AB is I naught sin alpha plus delta. So for very small values of the angles theta, because in practice the value of the theta will be very less, this is even in very less than 1 degree in practice. So very less angle error is produced. That's why when the value of theta is very less, I can replace tan theta, I can write in terms of theta only. That means for very less value of the angles, tan theta will be equal to theta. You have to remember here the most common mistake the students do. This theta is in radians. You can represent in radians, not in degrees. Please remember this one. So in place of tan theta, I can replace with theta in radians will be equal to I naught, because that BC is I naught cos alpha plus delta divided by n times of Is plus I naught sin alpha plus delta. This is in radians. So in practice, the value of I naught is far less than n times of Is. So this denominator I can replace with n times of Is. Getting it? Then this becomes theta is approximately equal to I naught cos delta plus alpha divided by n times of Is. Again same way I am expanding this one and then replacing with the magnetizing component and the core loss component, because we know I naught, because cos A plus B is cos A cos B minus sin A sin B. So this I can write as Im cos delta minus Ic sin delta, because I naught cos alpha is nothing but Im, I naught sin alpha is nothing but Ic. I have just replaced here. Okay, remember this angle is in radians, not in degrees. If you want to convert this to degrees, you can convert radians to degrees by multiplying with 180 divided by pi. So I have multiplied 180 divided by pi. So then this angle error that converts to degrees. Ideally this theta should be equal to 0, but in practice it is not 0. So again same thing here. So practically the value of the delta is very small. So cos delta can be taken as 1, sin delta can be taken as 0. So when you substitute in this equation number 8, that equation number 8 becomes theta is equal to 180 by pi into Im by n times of Is is in degrees. So we can tell that the phase angle error is mainly introduced due to the magnetizing component of the no load current. This is because of the magnetizing component of the current. Again this is also interview question. The phase angle error is mainly introduced due to the magnetizing component of the current. And the second one, the core loss component of the current is responsible for the ratio error. So please remember this one. So in practice, if you want to decrease the errors, what should I do? I have to decrease the terms Im and Ic. Even if you take the actual values, you can see theta is depending on Im and Ic. And similar way that the value of the ratio error, that ratio error also we got it as Im sin delta plus Ic cos delta by Is. Again it is again depending on Im and Ic. So we have to decrease this value of the no load component or Im and Ic in practice. So that's why practically when you are designing the current transformer, you have to take that your core should be designed like that. It will take the minimum magnetizing component of the current and it will have minimum iron losses, and the leakage reactance in the primary and the secondary should be as minimum as possible, so that the value, because this value I told you, the delta, the secondary phase angle will be as minimum as possible. So this is possible when the leakage reactance is made nearly equal to 0. So these care should be taken care while designing the current transformer. I hope up to here it is clear to you. So remaining topics, because as it has already taken so much time, the remaining topics, that is characteristics of the current transformer, that is how the characteristic of the CT are changing with the change in the load, power factor, frequency and other parameters, and what are the different types of current transformers used in practice and what are their design considerations. Those things I will discuss in the next class. If you have any doubts related to what is discussed today, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you very much.